My name is Ella Wesson, and I engineered one layer of a two-dimensional acoustic bandgap material and reconstructed the sound pressure field using acoustic holography. For some background knowledge, sound travels in compression waves, so the speed of sound depends on the medium through which it's traveling. Now, acoustic crystals are arrays of material. These materials contrast in their indices of refraction, meaning that the speed of sound is very different between the two materials. Acoustic crystals are characterized by band gaps, which are areas of space within the crystal where sound at a certain pitch cannot travel. Their applications include acoustic cloaking, which is a stealth technology that's very useful in the military. Acoustic holography is a method of mapping out sound waves in three-dimensional areas. I decided to use a method of acoustic holography which tracks the phase, which is the direction, and the amplitude, which is the loudness of sound waves. So after deciding to use that method of computational holography, my next step was actually engineering an acoustic crystal. I wanted to make one that was very cost effective, so I decided to use balloons. I filled balloons with two different gases, helium and sulfur hexafluoride. The speed of sound in both of these gases is very different, which is ideal for an acoustic crystal. I filled up the balloons with helium and sulfur hexafluoride, and I took scans of a single helium balloon, a single sulfur hexafluoride balloon, and a grating of them alternating. This is what that grating looked like in real life. On one side of that, I played sound through a speaker, and on the other side, I had a microphone, which was collecting data about the amplitude and phase of the waves at each point in that area. Then I used Python, which is a coding language, to analyze my results. These three holograms are all front-facing views showing the phase and the amplitude of a single helium balloon, single sulfur hexafluoride balloon, and a grating of them alternating. This here is a top view hologram. What's interesting about the top view is that it gives us insight into what's actually happening with the direction of the sound waves a little bit more. So sulfur hexafluoride, when there's a single sulfur hexafluoride balloon, sound actually converges, so it creates a converging lens. And when there's a single helium balloon, sound diverges, which means it creates a diverging lens. So when you put these balloons alternating side by side, it creates a really interesting pattern, which is characteristic of an acoustic crystal. So in the end, my project was successful in both of its goals, creating a cost-effective acoustic crystal, and then also confirming that the properties I expected were indeed there using this method of acoustic holography. Thank you so much for listening.